In the first video of this trilogy about Ramsey numbers, we use a very sneaky trick of proving that all 18 vertex graphs work to guarantee 4 vertices all connected in red or green. So our task today is to construct a 17 vertex graph where no 4 vertices are all connected in green or red. The counterexample for our 3-3 looks very symmetric, and this counterexample should be pretty symmetric as well. We are definitely not drawing the graph because it would be very messy. So instead, we label the vertices as 0 to 16. In the following argument, we might have something like vertex 19 appearing, but don't worry, it is just the vertex 2. Just divide the vertex number by 17 and take the remainder. In other words, we are working modulo 17 for the vertex number. Now the graph is constructed like this. We color the edge green if the endpoints have vertex numbers differing by 1, 2, 4, or 8. So for example, the edge connecting vertex 1 and vertex 16 is green, because vertex 1 can also be regarded as vertex 18, and then the difference in vertex numbers is 2. And so we should color this edge green. And we color the edges red otherwise. This is a very symmetric construction because all symmetries, including both rotation and reflection, preserve distances. So if the edge is colored green, it will also be colored green after the symmetry because the color scheme only depends on distances. But why does this construction work? Let's suppose we look at a particular vertex with vertex number v. The vertex is connected to the following vertices in green edge, those with vertex numbers differing by 1, 2, 4, or 8 as defined. And now, consider any 3 of these 8. Together with vertex v, we want to show that there must be one of the edges among these 4 vertices not green. But checking all these cases is still very troublesome, so we use some tricks to reduce the number of cases we need to check. In all cases, we can always choose a vertex v prime so that the 4 vertices in consideration is v prime and 3 of these 4 vertices. Because of rotational symmetry, we can always minus all the vertex numbers by v prime, and get that we are simply considering the vertex 0 and any 3 of 1, 2, 4, and 8. Now if 1 is selected, then either 4 or 8 or both are selected. But if 1 and 4 are selected, then the edge joining 1 and 4 is not green. And also, the edge joining 1 and 8 is not green. If 1 is not selected, then that means 2, 4, and 8 are selected. But then, vertex 2 and vertex 8 is not connected in green. So in all cases, no 4 vertices can be all connected in green. We also need to check for the red edges in a very similar way. Again, we simply have to consider the cases where one vertex is 0 and choosing 3 out of 3, 5, 6, and 7. It is simply a routine check that in all cases there is an edge that is not red. So this graph does not have 4 vertices all connected in green, nor any 4 vertices all connected in red. So we have proved using an explicit counterexample that R44 has to be larger than 17. But we also proved in the first video in this trilogy that all 18 vertex graphs work using a sneaky trick, so it has no choice but to be exactly 18. If you enjoyed this video, give it a thumbs up and subscribe to the channel with notifications on. See you in the next video. Bye!